I wanted to take a second today to go over the Earth's layers. First off, we need to know that there's two ways that we can look at the different layers in planet Earth. The first is by composition, and we can see that over here. Composition means the materials that Earth is made out of. When we think about composition, we're thinking about things like the types of rock that we'll find at the different layers here in planet Earth, or we might talk about the particular elements from the periodic table that we'd find at the different layers within Earth. So if we take a look, we have three different main layers here. The crust, which is the thinnest part, we can barely see it. It runs here along the outside of Earth. The crust is mainly made out of granite or andesite. It also has a lot of basalt in it. It's a very thin layer. If we look at kilometers, it's only 0 to 45 kilometers thick. So really thin. Interestingly, we've never managed to drill or go deeper than the crust because the amount of heat from the Earth's core prevents us from checking out through drilling any further than this. And we're going to talk a little bit as we go to the other side and look at the response to stress. We'll talk about that in a little bit and talk about how we know what's inside of Earth despite the fact that we've never been further than the Earth's crust. So again, that's right here, and the crust is made of granite, andesite, and basalt. The mantle is the next layer. It's right under us. Peridotite is the main rock that we'd find in the mantle. It runs from 45 to 2,900 kilometers. So from here to here, and it's kind of our middle layer here. You can see it's a lot thicker, and again, we've never been to the mantle. We know nothing about it directly. Everything that we've had is from evidence that we've found from other places and other methods. Lastly, we have the core, the very center of Earth right here. The core is primarily iron, although it does have some sulfur. It's 2,900 to 6,371 kilometers thick. It's all center, so it's a ball. Again, we can't get down there. It's way too hot. The outside of this core is made out of a molten material, but by the time we get to the middle of the Earth's core, it's solid because of all of the mass of Earth pushing down on it. Despite the fact that it's really hot and we think those things would be melted, they can't be a liquid because they're being shoved together too closely to be a liquid. We can look at it a little closer by clicking right here, and we can see one other piece of information, and then that's that our crust is made of two parts, the continental crust and the oceanic crust. You'll notice that the oceanic crust has blue on top. That's because this is the part of Earth's crust that's under the oceans. It's the thinnest part of the crust. Then we also have the continental crust. This is going to be the part of Earth's crust that's under land. That part of the crust is thinnest anywhere we have flat land, and it gets thicker under mountains. So in a way, as it goes up, the taller it is here, the deeper it also goes down. And then again, you can see that the mantle is everything underneath of that. If we take a look at the other side, we can take a look at response to stress. Now, when we talk about response to stress, this is going to be the physical reactions that we see and the physical things that we see. So we're talking about wavelengths and how waves pass through Earth. That's a lot of what we're doing. It's a lot like how bats use echolocation or subs use sonar to navigate. We can use the way sound waves and waves pass through Earth to know a lot about what's inside of Earth. So that's a lot of our observations come from that. We also, physical evidence could include things like what we see coming out of volcanoes and how volcanoes react, the movement of the ocean floors, and even now we're also seeing how drilling and fracking change earthquakes and how the Earth is moving. That also tells us, again, response to stress. So stress is anything that I guess causes change to the Earth. So we're thinking earthquakes, drilling, change, trying to be changed. So we have different layers here. The lithosphere is the outside layer of Earth. and it's also the thinnest layer of Earth here. And it's really, really strong. It's the crust. It's our solid part of Earth. And again, very thin, 0 to 100 kilometers. Now you'll notice if we look over here, the, the lithosphere is a little deeper than the crust. The crust only goes down 45 kilometers, but the lithosphere is about double that. It goes down to 100 kilometers. So that tells us that the way it reacts and what it's made of don't match up. Kind of interesting. Because again, this is the ingredients over here. So the ingredients on the top are one thing, and down a little lower are another thing. But the way it reacts when exposed to stress all means that it acts like a solid. And you know what solids act like. Think about anything around you. Think about your desk, your table, crackers, candy, any of that. Anything that's solid, absolutely solid. Glass, it shatters. That's what we think of when we think of the lithosphere. Now the lithosphere floats on the asthenosphere right here. The asthenosphere is kind of a weird substance. The asthenosphere could almost be, they describe it here as plastic. Plastic means that we could move it around. It's kind of like a real thick Play-Doh. Deformable means that it can be that we can change the shape. It can be deformed. Weak means that we can make its shape change. So it's what both those words mean. So this layer can move around and change shape. It's somewhat soft. So it's not really a liquid. Think of it more like a Play-Doh or silly putty substance. And this layer goes from 100 to 660 kilometers down. Now this is the layer that our continents float on. And so our continents and continental drift happen due to the asthenosphere being this movable type of layer. So we have the solid layer, the lithosphere or the rock sphere, sitting on top of this weird, movable, almost liquid asthenosphere. Now, as we go further down, we now are going to run into the mesosphere. Meso reminds me of middle, and you'll notice that middle definitely describes this layer. It's right here. It's a lot thicker than the other two that we saw. It's a solid layer. It's 660 to 2,900 kilometers down. And again, we're finding out that it's solid or liquid by looking at how waves pass through it. Earthquakes are a great source of information. We could look at if an earthquake happens over here, we could see what happens on the other side of the world and take readings. So it tells us a lot about that. We know how waves travel through solids and liquids. Here up on Earth, think about if we made a wave pass through honey or a wave pass through water. Think about how sound sounds different in a swimming pool versus if you put your ear up against a wall versus how it sounds just listening. That is the kind of stuff we're looking for, listening to sound and earthquakes. Again, that's telling us a lot about the response to stress of these different layers and if they're a solid, are they a liquid, what are they? How solid are they? Are they in between? We know all of this from looking at how the Earth responds to stress. Now when we get to the outer core, this is again, if we look at composition, the cores are mostly iron part of Earth, and it's how we get our north and south pole, and the magnetic lineup of planet Earth. It has to do with this iron core. And the outer core is liquid. Now the liquid part of the molten flowing outer core goes from 2,900 to 5,150 kilometers. When we get past 5,150 kilometers, we notice the inner core becomes solid. And that's, again, as I mentioned before, everything here, we have all of this pressure here from Earth pushing down on this layer. And a liquid means the molecules are spread out enough that they can move around. Well, when they're under this much pressure, they can't move. It's kind of like being a room full of people. If there were so many people that you couldn't move around, that's exactly what happens to these molecules. There are so many molecules being pushed together so tightly that it has to be a solid. It's really super hot here. I mean, that's the hottest part of our Earth. However, it can't move. Kind of weird. I know it's not what we expect. And the core goes from 5,151 to 6,701 kilometers. And then we've reached our last layer. Now we can look at this part, the response to stress, this way. You'll see again that the lithosphere, the strong solid layer, is most shallow out here under flat land or under ocean, and it becomes deeper when we have stuff piled on top of it. Think about the amount Earth has to push back to hold this. It has to have a stronger base down here to hold all these mountains up. So that's why we see it deeper under the mountains. And then you can see how the asthenosphere kind of dips down here. So let's take a look at that with this side combined, and you can kind of see how those two compare. Again, this is the crust that's made out of granite, andesite, and basalt, and this is the lithosphere. So it's solid all the way down to about here, but this part's made out of granite, andesite, and basalt, and this part of the lithosphere, when we look at it, the part that runs right in here, this is peridotite, so different materials. So that's why we have two different ways to describe the layers of Earth, and that's why you've seen two different sets of names to describe the layers of Earth. For the remainder of this, I'm going to use another interactive from Harcourt, and I'm going to let you take a look at this. You can read about the thickness, the density, so how close those molecules are packed together, and the continental crust, again, the part under land, and you also see the density under the oceanic crust, which is the density of the crust that's under ocean. I'm going to let this go ahead and read to you for the remainder so that you can hear that.
Play audio button is typically thinner and young. Click on the diagram to find out more about the layers of the Earth. Crust. Roads, buildings, trees, they're all on Earth's crust. Like the crust on a loaf of bread, the Earth's crust is thin compared to the rest of the Earth. It is less than 1% of the Earth's mass. In most places it ranges from 5 to 100 kilometers in thickness. At ocean ridges it is thinner. The crust under continents tends to be thick, with the very thickest crust found at mountain ranges. Where there are tall mountains, the crust goes down deep. Even though continental crust is thick, most of it is not very dense. Crust under the ocean, on the other hand, is typically thinner and younger, but very dense. So when plates of continental and oceanic crust meet, the dense oceanic crust often slides under the continental crust. Lithosphere. The lithosphere includes the crust and part of the upper mantle. Rock in the lithosphere is solid, like the rock above it. Litho means rock, and that's what this layer is about. The huge rock plates of the lithosphere carry the world's continents and oceans. As these plates move and collide, mountains are built, earthquakes are triggered, life on the crust is shaken up a bit. How can something that big move? The lithosphere floats on a layer of soft rock that can flow like taffy, the asthenosphere. Like the crust, the lithosphere varies in thickness. It can be quite thin around places where the seafloor is spreading. Asthenosphere. Astheno means weak. The rock here flows slowly like putty or taffy. Pretty slow in terms of humans, pretty fast in terms of rock. Mantle. The Earth's mantle is made up of the lower part of the lithosphere, the thin asthenosphere, and the thicker lower mantle. Together, these layers are about 2,900 kilometers thick. There is a balance in the Earth between heat and pressure. Heat makes the rock more fluid. Pressure makes the rock more rigid. So changes in heat and pressure in different parts of the mantle affect the characteristics of the rock. On the whole, rock in the lower mantle does not move as quickly as rock in the asthenosphere. But slow as it may be, motion in the mantle has a huge impact on the layers above. Heat rising from the core creates powerful currents in the mantle. As rock becomes hot, moves upward through the layer, cools, and sinks back in the layer. The motion helps drive the movement of plates above the asthenosphere.